One day, one day there was a fire in a wastebasket in the office of the Dean of Sciences. In rushed a physicist, a chemist, and a statistician. The physicist immediately starts to work on how much energy would have to be removed from the fire to stop the combustion. The chemist works on which reagent would have to be added to the fire to prevent oxidation. While they are doing this, the statistician is setting fires to all the other wastebaskets in the office. "What are you doing?" the others demand. The statistician replies, "Well, to solve the problem, you obviously need a larger sample size." And we will be talking about samples and sample sizes in our lesson today. So, why sample? First of all, let's assume you're on the prom committee and you want to know how many tickets you will sell so you can work on the budget. Well, what do you need to do? Well, first of all, you're going to start with your population of interest. Is everyone going to buy prom tickets? So you're not going to sell them to the kids in middle school, and you're not going to sell them to the kids in college, except in special cases. The people who are going to buy the prom tickets, those are the group we want information about. That would be primarily the juniors and seniors at Cedar Ridge. So we need to create a question to ask them. And if you have a bad question, you're going to get bad results. So if you mess up on the question, everything else doesn't matter. So what makes a good question? It needs to be clear, and it needs to be objective and non-persuasive. For example, how many tickets will you buy for the prom? Very straightforward question, and you can make good questions, but you can also make bad questions that introduce bias. So this is an interesting project two of my students did the previous year. Do you support the ability of industry experts to provide technical testimony and advice to legislators to improve lawmaking? Do you support the ability of corporations to freely influence lawmakers? So they asked question 1 and question 2. They're both kind of asking the same thing. But when they did their sample, their survey, they found that question 1 had a lot of yeses, but question 2 had a lot of no's. What was doing this? This is called response bias. When a question, so the way the question is worded, or who the interviewer is, influences the response. So, for example, you could have a guy asking a question, but someone else might have a different response if a girl asks the question. Okay, so that's response bias. We have to be very careful about the question. So now let's say we get our question, which is how many tickets will you buy for the prom? Well, couldn't we just ask everyone? And we could. This is a census where we attempt to collect data from every individual in the population. And when we have numbers that describe a census or a population, those are called parameters. Parameters are usually unknowable. By the way, they can change. So, for example, if you ask this question of every student at Cedar Ridge in September, you're probably going to get a different answer in October. And then you'll probably get a different answer in March. And maybe somebody will break up and not go to the prom. And so you might get a different answer in April. So parameters are usually unknowable and they can change. That's part of what makes them unknowable. So if we're talking about prom, the parameter would be the number of tickets to be purchased. Another example of a parameter could be the average SAT score for Cedar Ridge. That's going to change from year to year. So the difference between parameters and statistics, if you recall from the previous lesson, we were using statistics, and those were measurements for the sample. Parameters are values or measurements for the population. And we do have different symbols depending on whether it's a statistic or a parameter. And when you are writing your responses, you need to make sure not to mix these up because that can get you in the end. All right, so what if you can't do a census? And a lot of times we can't. Why? Well, it's difficult. It's time consuming. It's usually expensive. And sometimes it's just impossible. For example, if I wanted to know how the Oreos tasted coming down the production line, you really don't want to eat every single Oreo. Then that messes up the whole production line. So what's our alternative? We can take a sample. And what makes a good sample? Well, it needs to be representative. And a lot of times representative means the sample looks very similar to the population. If you're tasting soup, as long as you make sure it's mixed up and you take a taste, it doesn't really matter if you have a huge ladle or a small ladle, as long as you have a big enough ladle that you can get, say, some of the potato or whatever's in there. So absolute size does matter, but if I'm sampling this pot and this pot, I don't need to do 5% here and 5% here. It's just I need a spoonful, and a big enough spoonful that I can get the chunks I'm trying to get. Now for us, at least 20, if not more, is a good sample size to start with. And you will learn later how to calculate exactly how big a sample size you need. It does not need to be a certain fraction of the population. And there is a peculiar thing. It should not be more than 10% of the population. Now, here's some mistakes that will get you a non-representative sample. A convenience sample. In other words, oh, let me just ask the first 5 people I see because I just need to collect data. Well, maybe the first 5 people you see are all in your AP Stats class, and they're above average, and they're really good at writing because you need to write in stats, so maybe that influences your survey. Maybe the first 5 people you see are juniors. Do you think you're going to have a different number of juniors who are going to buy prom tickets compared to seniors? Most people wait till their senior year to go to prom. Some juniors go. You could say, well, let me select the respondents myself. So you're like trying to do a judgment. Well, this is bad because you tend to avoid the extremes and you favor what you expect. Okay, well, why don't we just let the respondents decide? We just let people who want to answer the survey, we'll just put some cards out and see who turns something in. Well, only people who feel strongly enough will respond. So this one actually favors the extremes. Let me go back up to that one. So that one favors the extremes. This one avoids the extremes. One other way to goof and not get a representative sample is to leave out part of the population. This is called undercoverage bias, when the part of the population is not even in the sample frame. What does that mean? So the sample frame is the group of people that you're going to pick from. If the part of the population is not even on that list, how are they going to get picked? So some examples, the people you may leave out may differ from those in the sample frame. And here's some examples. If you sample households, you're leaving out the homeless and people in jail or people traveling. If you sample landlines, you leave out those who only have cell phones. So you have to be very careful with your sample frame. So how are we going to go ahead and get a good sample? Well, first of all, sample frame, that's going to be an issue no matter what we do, whether we use good sampling technique or not. So you want to make sure you have a good sample frame. But let's say we get a good sample frame. How do we get a good sample? Well, we're going to learn from prize giveaways. How do we select prizes? We think a random drawing seems fair because it takes the personal decision out of the selection process, the individuals. No one's to blame. It's just chance. And one of the best ways to do it is the hat method. And another way to say it is a simple random sample, or SRS. So you put everyone's name in a hat. That's your sample frame. It's all the people's names that are in the hat. And you stir. Why? Well, it's kind of like stirring your pot of soup. If you don't stir, then the person who puts in their name last, or the last person to get in the hat, has sort of an advantage over people at the bottom of the hat. And then basically you stop drawing when you hit the sample size that you're going for. This is the gold standard for a simple random sample, and you will usually not get dinged. In fact, it's very hard to ding the hat method. So this is a good one to use. As long as it's reasonable that you could actually put everybody's name in a hat and draw, you are totally allowed to use that. All right, so we talked about bias, and now we have the gold standard. So let me talk a little bit about sampling error versus bias. So when you are doing sampling, you're going to get different answers on your sample, all right? This is just due to chance. Bias is the issue where there's something wrong with the design. So bias means we're getting a little off from the true value. So this is biased with not too bad a sample error. There's very little variation. This is what we'd love to get, very almost close to the true value, the parameter, and very little variation. But sometimes you're going to get a lot of variation in your sample. And this is worse than this. Both have a lot of variation due to natural variability, but one is kind of off of the answer. Whereas here, if you took the average of these, you'd be very close to the bullseye. Okay, so now we learn how the hat method can be used for samples, but should we use it for all samples? The problem is sometimes your sample frame will be quite large, so it might need some big hats, and it's going to be time consuming cutting all those little pieces of paper, making it pretty impractical and killing a lot of trees. So what can we do instead? We can actually assign a unique identifier to each individual in your sample frame, either student IDs, line number works pretty well, and get a list of random numbers, either from a random number table or a random number generator. Use the outcomes from that list to select the sample. Explain any digits which will be ignored. So which ones are you going to ignore? And ignore the repeats, because we don't want to have, you can't have the same person in the sample twice. They can only be once. And I should say individual because it's not always people. And you stop when you get to the desired sample size. So let's go ahead, and sometimes it sounds really easy, and there are different ways to do it. Sometimes it can get kind of complicated depending on how you set it up. So here I have the example in your notes. An 8-floor hotel with 30 rooms on each floor has 96 of its rooms facing the ocean, another 48 with a partial ocean view, and 96 facing inland. Room numbers have the first digit from the floor number and the next two digits from 1 to 30 for each floor. Rooms facing the ocean cost the most, partial ocean views next, and inland rooms the least. If the hotel manager wants to survey 20 guests, how would he select them using a simple random sample? So here on this screen, I'm actually going to use the room numbers. Actually, the easiest way is to just take the rooms and number them 1 through, let's see, how many do we have? 96, 96. That would be basically, hold on a second, I'm going to make this easier. 244 rooms, right? So you could just go 1 through 244 and generate numbers from 1 through 244 and ignore anything else that's outside of it. But you can also use the room numbers. So I'll show you how to do that. So you select 3 digits for each room. The first digit represents the floor number, and the second digit represents the room number. Ignore all outcomes above 830 because there are no rooms 831 or 9, whatever, because it's only 8 floors. Also ignore anything below 101 because in the US we don't start on floor 0. In Europe they do, but we don't. Also, you want to ignore the following ranges where there are no room numbers corresponding to it. So 131 to 200, 231 to 300, 331 to 400, etc. Now, since we cannot select the same room twice, we got to ignore repeats and keep gathering room numbers until you have 20 rooms to survey. So you can see it's probably easier actually to go 0 to 243 and just randomly pick from there. So there are different ways you can do it. This one's a little more complicated with the room numbers because there's so many different ranges you have to ignore.